during this internship, but also more generally what I'm working on for my master thesis. So I like Mozilla to implement my research ideas and use that to empirically evaluate how well that really works. And some of you might know me from last year when I interned in London. Okay, so my topic is mostly about doing machine learning in a privacy-respecting way. And currently there's sort of a conflict between machine learning and privacy. Because generally it works by collecting a lot of data, putting it on a server, and then training on that server. And if that data is private in nature, then as a user you don't really want to give it away. So for companies this is a pretty bad situation, because it either means that you collect data that users don't really want to share, or you can't even do machine learning at all. So there's pretty much two solutions to this problem. The first one is differential privacy, which is what I explored last year. And here the idea is that you randomize the data before collecting it. And if you randomize individual data points, you can't really make conclusions about individuals anymore, but you still might be able to figure out general statistics. But for machine learning, this doesn't really work that well because you're training on randomized data, which might be difficult to do. So to get really good results, you would actually want to directly train on the data and not on some randomized version. So originally we had this sort of centralized system where we collected data and trained on a server. And if we go the entirely opposite route, we could do a completely decentralized system where we only train on the user's computer. But that's probably also a bad idea, because users individually don't really have that much data, and so you're not going to be able to train really good models. So you really want to do something in between, which is federated learning. So here the idea is that we're pretty much moving the parts of the algorithm that touch the user's data to the user's computer. And then instead of sending data back, users sort of improve the model locally using their locally available training data, and then they only send back abstract model improvements. And most machine learning algorithms work in an iterative way. So they repeatedly look at data and improve their current solution a little bit. And they start off from some random solution. So this fits pretty well to federated learning, because in each iteration, when we want to improve the model, we basically sample a subset of clients, for example, K clients, and send them a current copy of the model. And then the clients use their locally available training data to improve that model. So they compute an update, and they only send back the update, not the actual data, which is much better for privacy because the update is very hard to interpret. So if you consider a neural network, it's like really, really hard to find out what an update actually means, and it's very hard to infer something about users' data. But we're still able to train a good model by doing that. And generally, this is nice for sort of user-facing applications. Because here users generate a lot of data just by implicitly interacting with the application. So for example, on a virtual keyboard, you get suggestions for what you might want to type next, and this is generated using machine learning. So there's a machine learning algorithm which learns based on text, and it uses the last 2 words that you typed to predict the next word. So you could train such a model on text from Wikipedia, but that's probably a bad idea because text or language on Wikipedia differs to the language used by people on mobile phones. So to get really good results, you would want to directly train on that data, which you can't really in conventional machine learning, because this is data that you really shouldn't collect. It's very private in nature. So with federated learning, you can still train a model based on that data, because you're only sending back sort of abstract improvements to a neural network. And if you think about it, this is actually pretty elegant, because while users are typing, they're generating a lot of data, and they're also labeling the data for us. And because as soon as they type the next word, we know the correct answer, so the neural network can check if it actually predicted everything correctly, and if so, with what confidence, and if not, it can use that information to update itself. So we have a really good feedback signal. And we can train a really good model by using a lot of data, while still not hurting privacy at all. So what I explained so far sounds pretty similar to distributed machine learning in a data center, but there's some additional challenges with federated learning. One of them is that the degree of parallelity is a lot higher than in a data center. So in a data center, you might have hundreds or thousands of compute nodes, but here we have to assume that we have millions of users. So the system needs to scale really well. And then we also have very little control over our data. So users are probably going to have very different number of data points. There might be users with a lot of data and users with very little data. And we also can't make any assumptions about the kind of data they have. So probably if you sample 2 random people, they're going to have very different data and thus generate very different updates. And I mentioned before that we are randomly sampling K users. So if we can't make any assumptions about their data, then this makes things very difficult, at least theoretically. And then there's also a huge array of communication aspects. So if you consider clients that could be mobile phones, then communication can be really slow. It might be unstable, devices might be offline, and so on. So there's a lot of things you need to take care of that you don't really have in a data center. And all these properties motivate a lot of the research in federated learning. And centrally, there's pretty much 4 major problems, which are like the individual chapters in my thesis. So there's optimization, which means that you want to reduce the number of iterations you need as far as possible. And this is really important because individual iterations might take a long time. So we need to wait until users actually generate data because we don't want to store the data necessarily. And that means we might need to wait 30 minutes or so. And if we need to do thousands of iterations, that's going to take a really long time. So it's worthwhile to take the time of thinking about better optimization algorithms to get that number down. Then compression is really important if you want to scale this approach. So if you want to use this with neural networks which might have millions of parameters, then you don't really want to upload all that information all the time, at least for mobile phones. So there's special compression algorithms you can use. Then privacy is pretty important. So I said that these updates are very hard to interpret, and it's hard to figure anything out about the user's data. But we really want to quantify how difficult it is, so you can be really sure. And this is actually where my internship project from last year kicks in. So you can apply differential privacy to this and randomize the updates that people send to the server. And by doing that, it becomes virtually impossible to figure anything out of the data. And you can actually also prove mathematically that it's virtually impossible. So you have a really strong guarantee. And from a theoretical perspective, this is really nice because it shows that you can still train machine learning models and get really good results. But at the same time, you can also prove that privacy isn't hurt at all. And then there's personalization aspects. So if you're already training on the user's computer, and if you're doing it in a way that's really good for privacy, then it's actually a pretty small step to also add personalization, at least engineering-wise. Okay, so this pretty much concludes the theoretical overview of my presentation. And we applied this to the Awesome Bar during my internship. And this is actually a pretty similar application to virtual keyboards. So people type some query into the Awesome Bar, the query is matched against the history, and then you get a number of suggestions. And the user clicks on one of them. And there's a ranking algorithm which basically chooses the suggestions that are displayed. And then again, there's this feedback signal that we also have in virtual keyboards. So we see what the user clicked on, and we can use that to optimize our model. So the current ranking algorithm is called frequency. It basically rates a number of features about URLs that you visited based on your history. So for example, if the URL was visited frequently or recently, or if it's a bookmark, it gives additional points. So it's sort of a scoring system. And for example, if you visited a URL in the last 4 days, it gives 100 points. If you visited it 90 days ago, it gives 10 points. If it's a bookmark, the points are multiplied by 2, and so on. So it's all sorts of magic numbers that people just chose because they seem reasonable, but they weren't really chosen in the data-driven process. So our project replaces all these constants by variables, and then we optimize for the variables. And we do that by checking what the user actually clicks on. So we get a really good feedback signal, and then the data that we actually send back are only abstract improvements. So we can't really figure anything out about the history and so on. So I can't really show results yet, because we're probably just launching it this week. But if you're interested in the project, you should definitely follow the Mozilla bug, which is where I'm updating the project. There should be a blog post coming out about the project in 2 weeks or so that I'm going to link there. Then my thesis is coming out in pretty much exactly a month. So in case anyone wants to read that, definitely ping me. And there's maybe also a paper that my mentor and I might publish in the industry track, for example, in the KDD conference. So the updates for all of that are going to that bug. Then all the code is open source. You can check it out on GitHub. And I've been blogging pretty actively about the topic. So there's a federated learning blog post overview, which goes into much more detail, or it's like much broader than this presentation could be in 10 minutes. So if you're interested, you can check that out. Otherwise, there's a differential privacy blog post from Alejandro and I that we wrote last year. And I blogged about some other techniques that we are using in the project. For example, rprop for optimization. And then finally, I need to thank a lot of people. So Sana, who was my mentor, was insanely helpful for this project. Whenever I had any problems or blockers, Sana was really, really helpful. Then I want to thank Katie for making it possible to return to Mozilla and write my master thesis here. Drew and Bob were really helpful with the client-side parts of the project. So especially the awesome bar specific APIs and converting everything into a web extension. And finally, Arcadius, who ported my Python code to Scala so that we could run it more easily on the server side. And yeah, that pretty much concludes my presentation. And if you have questions, I'm available now or anytime on IRC.
How are you going to evaluate the effectiveness of the model on the awesome bar?
So there's several metrics we use. For example, we check how many characters someone types before they choose a suggestion, and we want to reduce that as fast as possible. So people should find what they are looking for quickly. Then we're looking at the rank of the suggestion that was chosen. So the suggestion that's chosen should be as far on top as possible. And then there's some other like machine learning specific parts that we are checking. So we have like a loss function that tells us how well we are doing, and we want to reduce this loss as far as possible. So it's like a combination of several metrics. Yep.
If one wanted to learn how to build the models, is there a good place to look? Because I'm interested in Federated Learning has a way that we could improve bug triage.
Yes, so like the second repository that I linked contains like more general simulations, and like they are meant to be reused. So in theory, if you have other data and you have some way of generating the data, you could use these to do that. And I think the blog post like gives a pretty good overview about how it actually works and so on.
Thank you.
Hi guys, I'm Pratiksha. I'm on the web payments team, and this summer I worked on implementing the payment interface in Firefox. Before I go into talking about the web payments project and my work, I'd like to talk a little bit about why this project is important and what we're trying to solve here by building a payment interface in Firefox. And here's a question for you. How many of you can raise your hands, have had this experience where you had to abandon buying something off the internet when filling multiple long forms during checkout got too time-consuming, or when you had to try and remember your personal information off the top of your head? Great, so we have all been there. Here's a stat on that. In this survey, out of 1,800 responses from adults in the United States, a whooping 28% abandoned checkout, stating too long or complicated checkout process as a reason for abandonment. That's a large number of people if you look at the size of the sample set, right? So what we gather from this is that long checkout forms continue to be one of the leading causes for abandonment. Despite these challenges, though, the e-commerce payment space is huge. There are millions of consumers buying stuff off the internet every day, and we can see that there's a huge opportunity for us to improve the user experience around web payments, and we can now do that using the payment request API. So what is the payment request API? The payment request API is a new W3C web standard being introduced to make payments easier on a merchant website. So it replaces the traditional ship-in address forms, bill-in address forms, and credit card forms with the browser dialog to efficiently get the data from the user to the merchant. So if you have an online store, say you're a merchant, and you'd like to accept payments from consumers trying to buy stuff off your online store, you can use the payment interface that is now being implemented on most major browsers to accept payments from the consumers. The goal of this interface is to not transact money from point A to point B. We already have services like Stripe for that. The main goal of this interface, I would say, is to improve the user experience around making web payments online. So we do this by loading necessary information that are previously stored on your browser in form autofill storage. We auto-load it onto the web payment dialog, and you can proceed to checkout. So if you add things to a cart and proceed to check out on a website that is using Firefox's payment interface to accept payments, a dialog window will appear, and if you already have addresses and card info saved in autofill, they will be auto-loaded for use in the payment page, and you can make payments by selecting appropriate information from the drop-downs, and then just with a single click, you can be done with the payment. So here's what I worked on this summer. So first, I worked on establishing a first-time user flow in the payment interface. So when a user who has no saved addresses or credit card information tries to interact with the payment interface, we may first have to take them on an onboarding flow to help them make the payment. We show multiple forms in a particular order, depending on their current state, so as to gather the necessary information from them to make their first payment. So some variables we consider during the onboarding wizard for first-time users are whether the user has saved addresses in the browser, or if they have saved credit card information, or if they're buying a product that needs shipping from the internet. So for example, if they're buying, say, an airline ticket, it's not a product that needs shipping, right? So in this case, we have to take care not to ask them for the shipping address, even if they don't have addresses saved. So technically, there are a lot of these workflows, payment workflows, and depending on the user state, we decide what workflow to take them on, what paths to take them on, and help them make their payment. So I have a tiny demo here. This is a very simple demo to show you how the payment workflow works. So the parameters I'm considering here are, say, the user does not have saved addresses. The user also does not have any credit card information saved, and the user is purchasing a product that needs shipping. So it's uninteractive. Okay, so the screen is uninteractive, so I think I will have to, not interactive, I think I'll have to skip the demo. Okay, so secondly, I worked on, building custom elements for the payment summary page. This was the second part of my work. So this is how the payment page looked like before I built stuff on it or for it. So this is the closed state. You can see the pickers. So there's the ship and address picker, the dropdown, and then the shipping options dropdown and the payment method dropdown. So this is what it looked like in the open state. So if you click on the dropdown, this is what it looked like. So why did we have something like this? So we wanted to support multi-line options in the dropdown. So we wanted to show the name on a single line and the address on the next line and have options that were very customized. So we had something like this, but then we ran into some major problems because of which we had to change the whole thing here, change the dropdowns to make them look different. So what were the problems? So having a custom element like this meant no keyboard accessibility. We'd have to implement it by ourselves in the custom element code. And there was also the problem with positioning the dropdown, something like this. So if you had so this is custom built, right? So if you had a lot of options, it would overflow off the payment dialog, and you wouldn't be able to scroll, because scrolling, you haven't implemented scrolling in your custom element. But if it was native, the scrolling functionality would appear automatically, right? And it also flows out of the payment page when there are too many options. And also native styling is just better, or that's what we think, because it also uses the colors from the native colors and stuff and makes it look nicer. So we had to change this to this. So this is what I worked on. I built a custom element that integrated the closed state with the native select dropdown. So as you can see from the slide, so we have the native HTML dropdown, but in the closed state, you would see a customized element. So something like this. So by doing this, we now have keyboard accessibility in the dropdown because it's native HTML, and we also have the dropdown's position well automatically, and we don't have to worry about scrolling because scrolling is taken care of, and native styling just looks better. And then I also worked on doing some visual cleanup with this, so this is what it looks like now. We still have a lot more work to do here, but this is what we have. So this is what we have right now in the open state. And what are some challenges I faced when I was working on this? So I had a huge patch. I was working on a huge patch, and that patch broke a lot of tests. So I had a lot of automated test failures to deal with. And then I also realized that the only way to get through this challenge was to work through the tests, see where they're breaking and spend time on them and just get them to work. And also, I was working on a fast-changing code base. We're building the MVP, which means that everyone was committing code every day to the code base, and I had to rebase every day and take care of my patch after rebasing and make sure my patch was still working after rebasing it on the other's patch. And the third thing I found challenging was debugging in 3 different scopes. So here we have the browser Chrome scope, which is the privileged content, and then there's the merchant page, which is in the content process. Content, which is the content itself, web content, and then there's the payment request dialog. So I had to write tests that went back and forth between these scopes. So that was challenging, but it was also very interesting. And finally, I'd like to thank the web payments team. Everyone was amazing, and helped me do a lot of work. And then my mentors, Matt and Emma, they were very helpful with everything. And Justin Dolsky, my manager, for giving me this opportunity to work on this project. And the Firefox team and all the other interns. I had a great summer with you all. And that's it. Do you have any questions for me? Does anyone have any questions? Okay.
What's the handoff like between the merchant and the browser and back? Does the Web Payments API kind of like take you out of the scope into the browser?
So if you are a merchant and you use web payments, as in you send a request to the browser, as in like when you click on checkout after you've had it stuffed to the shopping cart, the merchant will send a message to the browser, and the browser will display the payments page. And it takes data off the autofill storage to fill the fields automatically, like the drop-downs that you saw. And when you click on pay, the control goes back to the merchant, and the payment is processed and information is given to them. So this whole thing is, we're just trying to efficiently take the data that's stored in the browser and give it to the merchant without a lot of work in between.
Cool, thanks.
Yeah. Does anyone else have any questions? All right, then. I'll just go.
Hello? Great. All right, great. Thank you all for being here. My name is Michael Rose. I'm the legal intern this summer. So one quick disclaimer before I start, I'm not a lawyer yet. So that being said, if I say anything that is not technically correct or if I happen to mess something up, just have it be known that I have 1 year of law school and I'm not yet licensed to practice in the state of California. So just going to put that disclaimer before I start talking about this. But yeah, so today I'm going to talk about a little bit of the basics of trademark law and how Mozilla interacts with that. And this goes to some of the work I've been doing this summer. So we've all seen these marks all the time. You know, the circle R, the circle C, the TM, maybe the circle P or the SM, a little bit less common, but those are also around. So we see these all the time. And as a matter of fact, we see them so often that they've effectively just become a punchline.
If you ain't first, you're last. You know what I'm talking about? That phrase, trademark, not to use the tradition of Ricky Bobby.
It was not very loud, but there's a trademark joke in there. Anyway. So I'm briefly going to talk about what those symbols actually mean and then move into how trademarks work. So copyright, which I'm going to go through very quickly, is the circle C or circle P logo. The circle P is specifically for sound recordings. I believe it's for a phonogram originally. So copyright basically protects like the stuff itself. So it's going to protect literary works, music, photos, and computer code. And copyright essentially grants the creator of those works rights to decide whether and under what conditions that work can be used by others. Those rights are usually granted for a limited period of time, though that may be a very long limited period of time, after which they enter the public domain and anyone can use them. This is where open source licensing comes into play. So things like the GPL or the Mozilla public license, these are copyright licenses. Yeah. And then we have trademark. So trademark is signified by the circle R, the TM for trademark, or the SM, which stands for service mark, which you use if you have like a service that doesn't necessarily have like a product that you are shipping to somebody. So trademark basically protects the wrapping of your product. So it protects things like logos, your product name, your slogan. Trade dress is a little bit different. I've grouped it under here because it's protected by the same set of laws as trademark, although it is technically kind of a separate category. Trade dress is things like the decor of like a Mexican restaurant chain, is that kind of protection. Basically, a trademark is something that allows you to distinguish the goods and services of one business from those of another. And this can even go to things like sounds and smells in certain cases. So, very high-level overview of how trademarks work. Basically, trademark law has two purposes, which the Supreme Court put very nicely in a case called Qualitex. So there's two purposes. The first is consumer protection. So the idea is that trademark protections reduce a consumer's cost of shopping and making purchasing decisions. So if you go out and you want to buy a certain brand of cleaner, you know if you see a certain trademark, that's what I'm buying, I'm getting the quality good that I expected. The other purpose is preventing unfair competition. So trademark protections ensure a producer of a good that producer is gaining the benefits of its work and that somebody else isn't benefiting by using their trademark from their reputation. So, let's see. All right. Then you have trademark registration. So R and TM are both marks that you'll see after trademarks. The difference basically is that the US recognizes what are called unregistered or common law trademarks. So these are trademarks that are just purely used in commerce, and you haven't necessarily registered them with the government, and you can still assert legal rights to them. So that's a TM mark. If you register a trademark with the Patent and Trademark Office, then you use the *R mark, and that essentially gives you a bit more protection, especially when you're dealing with like federal courts. So trademark infringement. Trademark infringement essentially is based on what's called the likelihood of confusion test. So if you are wondering if a new trademark infringes on an old one, essentially what you're trying to determine is, are these two so similar that a consumer would confuse one for the other? Now, there's a number of cases that kind of deal with this principle. A very well-known one, although it's not binding everywhere, is called Polaroid versus Polarad. You might guess what that trademark dispute was about. And this looked at a number of factors, things like how similar are the trademarks, has there been actual consumer confusion, and how similar are the two goods being sold. So that's basically what you're looking for to determine if there's trademark infringement. And then lastly, you have trademark fair use, which allows you to use someone else's trademark without incurring some kind of like legal liability. And there's two kinds. Descriptive fair use, which usually happens when someone has a trademark on a word that has like a kind of everyday other meaning. So like one example of this was that there's a candy company that trademarked the term sweet tart as a candy. However, a cranberry drink maker could still use the term sweet tart to actually describe their drink, which was sweet and tart. And then there's nominative fair use, which is essentially you are directly referring to someone else's goods, but not in such a way that you're implying that you're that company. So this might be something like a auto repair shop has a sign that says, "We repair Rolls-Royce cars." So they're advertising that they repair Rolls-Royce cars, but they're not pretending to be Rolls-Royce. There we go. So Mozilla's trademarks. So Mozilla is open source, which means we really don't have a lot of IP. We have a few patents in the video codec space, which we immediately license out freely. We do have Pocket now, which does have some closed source IP. But other than that, what we really have are our trademarks. We have the logos, we have the names. So this is really a balancing act, because we want to be sure that these trademarks are marks of security, they're marks of a quality product that internet users know. But we also, of course, have the many Mozilla communities and people that do need to use these trademarks. So it's a little bit more of an interesting balancing act than if you look at like a Facebook or like an Apple trademark policy, which just essentially says, no, you can't use it, don't even think about it. So we currently have a trademark policy. What does that policy look like? Well, this is basically what our current policy looks like. This is not actually something I made for this presentation. I made this earlier this summer so that I could keep track of all of the different trademark pages we had. And I'm pretty sure I didn't catch them all. So we essentially have like a main trademark policy. However, we have a lot of other material that is either linked to or in wikis or all over the place that deals with how we use trademarks and how we let people use our trademarks. Sorry, having clicker issues. There we go. So there's about 30 or 50 pages of material, depending on if you count certain wikis or not. There's a lot of duplicates, there's a lot of broken links, out-of-date material, draft documents floating around. Just last week we had someone asking about if they could use Firefox in a TV show. and they had an old document that essentially said, you can freely use Firefox in a TV show, don't even need to ask us. And we realized, hey, we do actually kind of want to know what show you're putting this in. You know, we probably would want it to be publicized, but we want to also be sure that we know where it's being used. So then the question becomes, how do we improve this? So the large project I worked on this summer, along with Jeff Garver and other people in the legal department, was to draft new trademark guidelines. And there are essentially two goals. One is that they're concise, excuse me. Obviously, we don't want people looking through 30 plus pages of material for the answers they need. And secondly, we want them to be clear. There are essentially two questions people ask when they go to a Mozilla trademark page. They want to know, what are our trademarks, and what can and can't I do with them? So those were the two things we really wanted to be sure that we did in drafting these new guidelines. So the new structure, as it currently stands, is there's essentially 3 pages. First, we have the main document, the Mozilla Trademark Guidelines, that outline what you can do with trademarks. Secondly, we have the trademark list. So it shows these are all the trademarks that Mozilla has. And lastly, we have a special document about distributing Firefox alongside Mozilla trademarks, and I'll talk a little bit about that in just a minute. All right, so the new Mozilla Trademark Guidelines. So there's essentially 3 sections to it. The first one is, when do I need permission to use Mozilla trademarks? So essentially, if you're using Mozilla trademarks in text or using them to link to our products, that's fine. If you're using trademarks to describe a Firefox add-on or a social media account under certain guidelines, that's also fine. Most other uses, though, are going to need permission. Then we ask, well, if I'm allowed to use a Mozilla trademark, how do I use it? And this is essentially a list of do's and don'ts. So it includes everything from things like, don't modify our trademark, so don't recolor the Firefox logo. Don't use Mozilla trademarks in your business name. Don't sell material with Firefox trademarks on them. Don't use them on sites that, deal in illegal activity, that sort of thing. And lastly, we have some special additional guidelines. So there are some specific guidelines that the branding department has for using the Firefox and Mozilla logos. And we also have some specific guidelines if you want to use Mozilla trademarks in relation to a Firefox add-on or in a social media account. Those essentially, the core of those is that we don't want somebody pretending that they are connected to Mozilla when they're not. So there's a difference between saying, for instance, an add-on called Firefox Video Enhancer, which implies that it's a Firefox feature, and Video Enhancer for Firefox, which implies that it is an add-on made for Firefox, not actually something that we've built. Then we have the Mozilla trademark list. Perhaps unsurprisingly, it's a list. So we have Mozilla word marks. So these are just the actual word that we've trademarked. So this includes things, of course, like Mozilla, Firefox, and also newer things like Firefox Rocket. We have 35 word marks if you include Pocket. Mozilla logos as well. We have 33 logos, again, including Pocket. Essentially, with this list, what we're doing is taking all the classic old, the Dino and the Firefox logo, and bringing in the new members of the family like Pocket and new versions of Firefox. And lastly, we have a document regarding the distribution of Firefox using Mozilla trademarks. So we have kind of a unique situation in that we encourage people to distribute Firefox, and we, of course, are giving it away for free. So anyone can download it, and it's open source under the Mozilla public license. So that brings up the question of how this then interacts with these trademarks that we're seeking to protect. So there's essentially two situations. One is that anyone can distribute unaltered copies of Firefox, and they can use our trademarks when they do so, so long as they don't charge for it and they're not modifying any files. Secondly, if you do choose to modify Firefox, which you can very much do, you do need permission from us to continue using our trademarks. So this includes things like changing the default homepage, or adding extensions, or going in and modifying the source code. If you do any of that and then try and redistribute it, you do need permission from us. This is essentially because we don't want people adding in bloatware or malware and pretending that it's pure Firefox. Again, this goes back to kind of that idea of consumer trust and ensuring that people know what they're getting when they download Firefox. So moving forward, we're continuing to review these policies and make sure that we have everything balanced out as it needs to be. We are going through and clearing out many reports of possible trademark violations that we've received. And lastly, we're better building a internal system where if you see something that you think might be a trademark issue, you can report that to us, and then we can look into it. Yeah, so that's essentially the new guidelines. Let me know if you have any questions.
So question for you about people who build Firefox and then use it in various distributions such as Debian and Raspbian and all of those. Mm-hmm. Does this change to these guidelines mean that we need to go and talk to these communities, essentially Linux and BSD distributions that are packaging and sending and distributing through their own repos, like through apt-get or whatever tool you want to use?
Mm-hmm. So if we have existing distribution agreements, I don't think there are any issues. Again, this section should also again come with a disclaimer that I'm the legal intern. If you do have serious legal questions, of course you can ask legal and they can give you the definitive answer. But yes, I should have put that on the slide.
What does the typical trademark violation or report look like? And are there any unusual cases that you can share?
Sure. So we get a number of violation reports a day. We have kind of a public web form. To be honest, a lot of stuff that comes in through it is spam because it's a public web form. But probably the most common report we get is like an update, what we call an update scam. So it's kind of like your classic pop-up or like a web page that pretends to look like Mozilla and says, you need to manually update Firefox, disable all your security and download this file. So that's kind of the typical violation. We also see things like people selling merchandise with Mozilla logos on it. We see, the other big common one is probably fake tech support. So people say, we're Mozilla technical support, call us and pay us a fee. That's probably the second biggest one, yeah.
I have a question from Portland. You mentioned in your permitted trademark uses, you mentioned social media accounts a lot, and I wasn't sure what that refers to. Is that like user groups or what? What kind of social media accounts other than ours are using our trademarks?
Sure. So that mostly deals with community members. So people who want to set up community, Facebook or Twitter accounts. And occasionally there are just groups that actually want to set up fans of Firefox. So those are mostly the cases that deal with social media.
From San Francisco. So you talked about how if somebody wants to take Firefox's code and modify it, they can't continue to use trademarks. But if they remove the Firefox logo and change the name, can they still use the code without any trademark violation? Can they make any changes that they want?
Yeah, so at that point, it's it's licensed out under the Mozilla public, the actual code is licensed out under the Mozilla public license. And this has happened. So, for example, I think, what's the name of it? There's been a few, WaterFox, I believe, is one of them. Occasionally you'll see this happen. So this is something that does happen occasionally. Cool. All right. Thank you very much.
I've been here this summer for an internship in the DOM team, and I'll be talking to you about standardizing inter-process communication in privileged JavaScript. I'll be also calling inter-process communication IPC just because it's much shorter. So first of all, you have to know the context of my internship, and it has to do with something called Project Fission. And Fission aims at making sure that every website origin runs in a separate process, because very recently we had the Spectre vulnerability, which allows many websites to escalate privileges if they're not running in their own separate process, and that can be very dangerous. So that is Firefox's answer to that problem. Chrome has very recently also released site isolation, and it's a very big, a very big challenge, because on average that would mean running about 100 processes for a regular browsing session. So it's a pretty big thing. And so in this context, we need a way, we need a very standard way to enable inter-process communication, just because if we're running 100 processes and we're not making sure that everything is very standard, then we'll run into troubles, definitely. So the current way that Firefox works, it uses a hybrid approach, which uses content processes. And basically a content process is a process running web pages, but it can run any amount of tabs, any amount of sites. And right now the default, I think, is, I mean, it varies on the systems, but basically you'll be running about 4 processes, and then the tabs will just be like shared, not shared, but like dispatched between the processes just to try to even out the loads. And so this is the current architecture. Then you have other processes on the side, like I think we have one for the compositor, or maybe not yet, but we have also like JavaScript, garbage collection, and stuff like this. And so what the Fission project aims to make things look like is having something like this, which is basically we'll still have the main process with the other processes, which don't have anything to do with running JavaScript and user code in the browser. But for the actual content processes instead, we'll be running each website in its own process. That can also mean that if you're using, for example, if Facebook is through, let's say, a like button, is running in 2 different tabs, then the 2 Facebook scripts will actually be running in the same process. So that's how we try to limit the amount of processes that we spawn. And so right now, we have a thing in place which is called IPDL, which allows us to to describe protocols and make the 2 like 2 processes communicate with C++ code across the process boundary using that language. So it looks a bit like this. It's actually pretty simple. So you describe a protocol, and then you describe a certain amount of messages that can go from the parent side to the child side, the other way around, or both. They can be async, they can be sync, they can have return values, anything you'd expect from the standard protocol definition language. And so the thing is, in Firefox, we use JavaScript also to run Chrome code. Chrome code is privileged code, which allows you, for example, to have an interface in your browser. The interface of Firefox is written in JavaScript, amongst other things. And so we might want to enable that privileged JavaScript code to also make inter-process communication between the parent process and the web page content processes. So yeah, just an illustration of what the current C++ code looks like using IPDL. Like, you have protocols exchanging messages, everything is fine. And right now, the only solution in JavaScript to communicate between processes is using something called the message manager. And the message manager only allows you to send basically JSON objects. And it doesn't restrict anything on the type of messages or the data or the structure that it has. So the very big problem is that you can run in situations like this, where you'll be sending a message and it absolutely doesn't have the shape or the form that the other process expects. And so you'll be running into big troubles, and everything will be checked at runtime, and that is very helpful. So my internship was basically bringing IPL to JS code, so allowing you to load IPL protocol files and then use them from JavaScript, so that you can basically use and the whole messages that were described from JavaScript. So the specifics of what I've done, I won't dive into specifics just because that wouldn't make sense for such a talk. But it was pretty challenging because I had to deal with code on 3 different levels. So first of all, we wanted to replace the current parser for IPL, which is written in Python, by a parser written in Rust. And so I had to adapt an already existing Rust parser and make sure that everything's fine, etc. Then I had to expose the syntax tree that was created by the parser to C++ so that C++ could do the inter-process communication. And then the C++ side exposes a JavaScript API through SpiderMonkey, which is the JavaScript engine of Firefox. It exposes a whole set of APIs that JavaScript code can use to communicate between processes. So it was pretty challenging in terms of finding my way around the code, making sure that I don't blow things up with the garbage collection, cycle collection, all that. It was pretty challenging, yeah. And so also a very big point of that is that it will enable you to load IPL files from while using artifact builds. So artifact builds are specific builds which are deployed. Basically, you have the whole C++ quad is already compiled into binaries, and so you download these binaries, and then you're able to simply code JavaScript and then package it into the final application. So this brings you much shorter build times, and it's basically made for JavaScript developers. And so the IPL files can be loaded using artifact builds, and that's a pretty big thing. So I'm sorry for putting code on the presentation, but I think it's pretty interesting to see how it's used because it's actually very simple. So I have a very simple protocol definition, async messages, sync messages, they just have a number coming in and out. And then there is an example, so on the left, of implementing the protocol in JavaScript. So basically all the sending a message is already implemented. You don't have to do anything custom for that. And you only have to register handlers for receiving messages. And so here, all my handlers simply add 1 to the number that was received. And you can see then on the right how to use it. So sending a sync message or sending an async message through a promise. And that is actually very easy to use. And so you're just able to communicate between 2 processes just using something that was defined beforehand using a very standard protocol. And that is very important. Also, so the fact that I had to test JavaScript on 2 processes communicating was also pretty challenging because you have to run a different debugger for each process. And that was kind of a nightmare sometimes. And so also the main point is that you have errors when trying to use these things from JavaScript. And you have these errors when sending the message instead of having to check the contents of the message that you receive with the message manager. That was really awful when trying to check that the object has the correct format. So right now you get proper errors when loading files, when sending messages, when trying to do stuff that you're, for example, deleting a protocol and then trying to use it. Everything is covered, and that's really good. And so this is only a small part of the whole IPL transition or fission project thing. Because so right now this, what I've done, only enables JavaScript to JavaScript communication between processes. Yeah, okay. Only enables JavaScript to JavaScript communications. And we might want in the future to enable JavaScript to C++ communication and maybe communication between Rust and C++. I mean, basically enabling communication between processes from any language to any language. That would make things much more flexible. We would also want to move the current code that's written with the message manager, and we work that into using IPL so that we have a stricter stricter message semantics for communicating between processes. Also, that can be used, the new IPL parser can be used for hooks for release management, because right now if you write IPL code, you will, and it generates C++ code, and if you have a problem in that C++ code, then it's really hard to go back to the IPL code that generated it, and so it's really useful to have that kind of tooling. And also, my whole work has still to land, but that should be solved pretty soon. So that's basically it. That's basically my internship, just allowing two JavaScript scripts running in different processes to communicate with each other in a very standard way. And it's going to pave the way for the whole Fission project to have good process separation for all sides, which should bring a lot of security and flexibility. So thank you, and if you have any questions, please don't hesitate. Okay, I guess that's it. Thanks. If you have any question in the meantime, you can still ask it.
I assumed you had the same question I did when I did the same thing. Yeah. But I wasn't sure. So just give me a thumbs up. Yeah, me too. Yeah. Eventually, probably. Right.
Good to go? Okay, great. All right, welcome everybody. My name is Sanjay, and I've had the pleasure of working on the Rust compiler for the last 3 months here at Mozilla. Specifically, I've been working on this project called Chalk, which is the new traits implementation in Rust. And if you don't know Rust or you don't know about traits, don't worry, because I'll get to all of that as I go along. So the Rust compiler is responsible for taking code that's written in the Rust programming language and turning it into instructions that your computer can understand. It takes lines of Rust code, performs some analysis, and then turns that into machine instructions. What I've specifically been working on is the analysis part, and so that's mostly what I'll be talking about today. Compilers do a lot of analysis on your code to make sure that it's correct. The type of analysis that I was doing is designed to solve a very specific problem. It's my job to detect when it's possible for a Rust program to have two different implementations for a single operation. Having two different ways to do something is really problematic when you're trying to generate code, because you want it to generate the same code every single time. Take sorting a list, for example. Yes, there are plenty of ways to sort a list in computer science, but once we've picked a way, we want our code to behave the same every single time. Even if our compiler gets updated, as long as our code stays the same, we expect it to produce the same outcome every single time. And so having only one implementation for any given operation is a really important part of this. And so we actually have given this property a special name, and it's called coherence. The Rust compiler actually already implements coherence, and so my job was to take that and re-implement it into the new traits implementation called chalk. So what is a trait? Well, remember those operations I was talking about before? A trait is a way to represent the operations that can take place on different types of data. A good way to think about it is that traits are the operations on types of data, and implementations are the way that those operations are meant to be carried out. A trait called sort could define the operation of sorting a list in ascending order. And its implementations could describe how we want that to be carried out for a list of integers, or we could add an implementation for a list of text strings or any other type of data that we wanted. So when the Rust compiler is given a list of operations and their implementations, it needs some way to figure out which implementations to use for a given type of data. Chalk is a new way for the Rust compiler to solve that problem, and it's a piece of software that's specifically designed to provide answers to certain types of logical questions. We can give Chalk a fact like Manish loves mangoes, and then define rules like a person eats mangoes if, or sorry, we could define a fact like Manish loves mangoes, and then we could define a rule like a person eats mangoes if they love mangoes, and use that to come to the conclusion that Manish eats mangoes. And so Chalk actually uses the fact that Manish loves mangoes, puts it into our rule, and is able to come to this same conclusion, just like we did logically. The benefit of using an engine like this is that we can process things in logic instead of having to write specialized algorithms for everything. We can model a lot of the different analysis that the compiler does using logic, which gives us a single general algorithm or a single general engine for computing these kinds of different things. So just a reminder, coherence means that there's only up to one implementation of a given operation for a given type of data. Well, how do we check that in the Rust compiler? We do two things. The first thing is that we limit every implementation so that it can only be defined in one place. And two, we go through every pair of implementations and we make sure that they don't apply to the same types. The first check is called the orphan check, and the second check is called the overlap check. The orphan check ensures that every implementation can only be defined in a single place. It does this by enforcing some specially designed rules called the orphan rules. The orphan rules basically say that if you're going to define an implementation of an operation for a given type of data, you need to do that either where the type of data is defined or where the operation is defined, but not in both places. That means that other people who use operations that you define can't implement them for types that you define, and at the same time, you can't implement your operations specifically for their types, since you don't necessarily know about them when you define that operation. This makes it so that there's exactly one place where an implementation can exist. And the way that this works now in the Rust compiler is that it has a specific algorithm that actually runs through all of the implementations in your program and tries to make sure that the orphan rules are satisfied. With Chalk, we can actually use our logic engine and ask it questions like, does this implementation satisfy the orphan rules? Chalk will then go through our Rust program and use logical rules to determine whether the answer to this question is yes or no. And so over the last 3 months, what I did is I took the orphan rules and I found a way to write them out using logic and figured out a way to take any Rust program and allow Chalk to come to the answer to this very question. The overlap check seems really simple at first, right? You take every pair of implementations in a Rust program and you check that they apply to the same types of data. The problem is that we actually need to do a little more than that, right? If we need to be able to account for implementations that haven't even been written yet. And so to actually make sure that an implementation doesn't and can never overlap with another implementation, we need to check it against every possible implementation in the world. Now, that's clearly infeasible, and so my job was to create some logical rules that described which implementations could possibly exist somewhere. And so to do this, I did a deep analysis of the kinds of implementations that could be added anywhere. And this was a really cool thing to try to do, because not only did I have to think about the Rust code that the current program might have or that the current program might depend on, I also had to think about other projects that could depend on the current program and think about how that interacts with these different rules. And so at the end, I came up with several rules to model all the different cases and mimic the algorithmic way that the Rust compiler was using before. Probably one of the coolest consequences of my work is that we now have these really well-specified logical rules for this property of the compiler. In the future, this might allow us to formally prove that this property holds for the Rust compiler as a whole. And it opens the door to implement other highly anticipated Rust features, such as specialization. And it'll even make it so that when we make changes to the compiler, we can clearly see the effects on these logical rules. So if you know Rust and you're interested in learning more about coherence and Chalk, I actually gave a much lengthier talk at the Bay Area Rust meetup a few weeks ago. I go into all the details of this and how it works with Rust code. And the video is online on the Rust YouTube channel if you want to check it out. I want to make sure I take a moment to thank my wonderful mentor, Nico Matsakis, my manager, Aaron Turan, and all of the colleagues and coworkers who helped me out throughout this term. I really appreciate how patient they were as I went through and figured all of this out and made sure that I did it correctly. Here's my Twitter if you're interested in talking about this online. Otherwise, I'm happy to take your questions now as well. Thank you.
I have a question about how the rule sets are implemented. Is it a domain-specific language in Chalk that is kind of like Prolog? I'm having a, well, yeah.
I can answer that question. So Chalk is an engine for solving logical predicates, a lot like Prolog, but using a language that's actually a superset of Prolog. And so we have our own domain-specific language for testing Rust code, but when it actually comes to writing the rules out and to implementing it in the Rust compiler itself, we just write Rust code that the Chalk engine knows how to use. Like, we basically use the engine internals directly.
Cool, thanks.
So, yeah. Anyone else? Okay, thank you very much.
isn't sharing.
Very weird.
Okay. Let's see, I can switch on. Let's see what we do. Switch to stop. Okay. Okay, and then and then now, whoops, sorry.
It's okay.
And then should be able to
make that big.
Yeah, let's see.
Okay.
If it would, there it goes.
Thanks. Yeah. Okay.
Is that good?
Okay.
Okay, perfect.
Yeah. So just when do we start?
It should be exactly 15, so I'll check with. I'll give you a thumbs up.
Okay. Okay. Say what? I'm too nervous. I don't do presentations. Y'all are enjoying this. Okay, are we good? Okay, yeah, okay. Hi then, my name is Kristen Wright. I've been working this summer with the low-level tools team. I'm working with Eric on representing DOM structure in the JS memory tool. Essentially what that means is the JavaScript memory tool before was mostly just representing GC collected objects from SpiderMonkey, and what we were able to do is make it represent much more in the heap than simply JS objects. So a bit of an overview about reporting memory on a web page. Memory reporting in Firefox lets developers see memory consumption of their work, lets engine developers see what kind of objects are taking up an excessive amount of memory or what kind of objects are behaving in a certain way. And also you can see how a web page is consuming resources at a specific instance in time, which is why we call it a snapshot. So when we report memory, we generate this web page snapshot of the page's heap and report the details of the elements on the page. We store this data in what we call ubiquitous nodes, or UB nodes as I will continue to call them from here on out. And we yield the UB nodes outgoing edges and traverse the graph to view any relationships between different reported objects. So how do you get an object to report for UB node? Objects that report their size and outgoing edges need specializations. We call these concrete specializations. You're going to hear that a lot. I'm going to talk about concrete specializations of different UB nodes. And so for garbage collected things in SpiderMonkey, because SpiderMonkey is a JavaScript engine, we garbage collect JavaScript objects. UB node can get the tracer edges from the GC participants. But what we did is we said, what about the elements that aren't GC things in the heap? How are we going to yield those edges? So to kind of preface that, when you report a data type as UB nodes use, again, a concrete specialization that takes a certain referent. This is a template, and we override methods in that template to specify measuring size, measuring the outgoing edges. And outgoing edges, when I say that, basically means what is this node related to in a graph when we take a heap snapshot. And then we can describe its relationship with other nodes that way. So an example would be, let's say we have a JS script or a lazy script. And so in JavaScript talk, that means you have a script, and a script actually has what we call a source text, which is actually a reference to the file that that script comes from. And so let's say a source text should be reported for a JS script. Well, a source text is not a GC thing. It is a file size. So we would have to attach a node to this GC thing when we present our graph in order for you to see the source text and see the size of it. And so going into that, there are other things that are not GC things, such as DOM structure. And DOM elements, they're not really GC things. They can't really yield edges by consulting the GC. So, in general, SpiderMonkey does not understand DOM structure. That's where it gets difficult to figure out where a DOM element is in the graph. However, what SpiderMonkey does is it creates JS objects that actually serve as reflectors to DOM elements. And I've got a handy little graph up here that kind of shows in the top right, a reflector object, how it has a compartment essentially that wraps an NSI supports, which is actually a DOM element, into a void star. So that's how we actually hide that DOM element in memory in a way that SpiderMonkey does not completely understand. So, however, UB node is a part of SpiderMonkey. So we can't just tell it to unwrap an NSI supports and measure that. UB node isn't going to know what we're talking about. It's a part of SpiderMonkey. It doesn't understand the structure of an NSI supports, of an NSI node. So that is where we have to connect the two and make them talk. So what we can do to do that is all JS objects have a runtime. And that runtime is actually accessible from XP Connect. So what that means is if you have a JS object that is a reflector object, XP Connect can see it, and it can see the other side, the DOM node that is hiding inside of it. So using a runtime hook, we can actually delegate the construction of a UB node back to the DOM structure. We can tell it from that side to build the node. And then the SpiderMonkey side knows that the node exists. It knows that there are some rules for using the node, but it doesn't necessarily know the type of the node. Because at the end of the day, the node itself is a vtable and a pointer, and that's all it really is. So it can, it's called ubiquitous node. It can essentially store any real type into it. And what you have to do, what your job is to do, is to specialize that so that you can communicate these different node types. So we can create a hook, construct the NSI node specializations from there, and attach their outgoing edges from DOM outside of the reflector object. So we know a reflector object can possibly hold a void star, which is actually an NSI supports. That NSI supports could be an NSI node, which could be many amounts of things that exist inside HTML. It could be a div, it could be a paragraph, it could be an image, it could be anything. So the NSI node could be extracted from an NSI supports to get that information of what am I. And the NSI nodes, in turn, actually have pointers to their siblings, to their children. So if you've got a text inside of a div, inside of a body, then the NSI node knows that its parent might be the body, and then its child node might be the text. So when we specialize an NSI node for UB node structure, we typically have it show up as, since NSI node is a superclass, essentially, of all of these different pieces of DOM structure, we can override a construct function that gives it instructions of here is how you build your specific UB node to measure your size. And so we can override that function. We can call that function not knowing exactly what its subclass is, but knowing that it might have an overridden function or a default function to just build an NSI node specialization. And then we can build that specialized node that has more instructions on how to accurately measure size, how to report its name, how to yield different information. So from there, displaying DOM nodes with useful information would be the next step, right? Because let's say we've got an NSI node, we know all of its children, we're also reporting its children, but if we just know them as a structure of, this is called NSI nodes, this is a node, this is a content, this is an attachment, that's not very informative to the user. But what we can do from there is UB nodes actually sort themselves by what we call course types. And course type can essentially be any kind of thing. It can be a string, it can be an object, you can just lump it into other, it can be a script. And we create a new course type specific to DOM nodes that has all of its instructions that it needs to give it descriptive names and to describe its structure in a visual manner. So what we're saying there is we already knew that these things exist, but we just knew that they were something that is not a GC thing. We can lump it into other, and we don't know what this is. But if we create a new type with new instructions on how to get a special name for it, we can yield more information. And the graph here is actually an example from when you run the heap snapshot, and you can look and see different DOM nodes and their names. I think there's an HTML body and an iframe there. So you can see how they go down the hierarchy all the way down from document, which is the parent node, to the HTML node. So another way to view this memory and to actually see how much we have added is the DOM node graph. And I've got an actual screenshot of the graph right here. And what we can see from there is actually the new course type is the light purple in the top right, and we've added all of that reporting. That's all memory that was not reported in the past and is now reported and in detail. So individual elements can be viewed from the graph. The graph is unfortunately very small from this view, but you can actually, in the memory tool, you can actually zoom in and see individual names. And it's sort of a visual representation to see how much memory is being used in comparison to other parts of memory. So when you're in the memory tool and you're tracing DOM elements, NSI nodes, again, they contain references to siblings, parents, etc. So they can trace and yield their outgoing child edges. So we've done that. And then viewing the graph can give a more detailed view of parents and children and the like. So when you look into the graph, you can actually see, if you're looking for a particular element, you can actually see where it is located in a file by, you know, we've got this input that's inside of a div, that's inside of a form, that's inside 3 other divs, that's inside the reflector node. So you can essentially see where in memory this is being held and how it is associated with these other nodes, which we were already sort of doing with JS objects, but we were not previously doing with DOM node objects. So, and then also measuring the size. I don't know how well known the memory tool is from the Gecko side, but we have another memory tool called About Memory, and we have a means to measure the size pretty well of a lot of Gecko objects. And the good news about that is that means we can also measure the size in the context of UBnode. We can already get the size, and then from UBnode, we can also see the shallow size of a graph and its associates. So we can see the size of an individual thing, which is the size on the right on the little screenshot, and then we can see the total size of that piece of information, which, so there might be something that, here's a div that's only 368 bytes, but its total size of all of the divs is 8,000 bytes inside its graph. And then you can look and see the graph, you can see where it's coming from, you can see the memory addresses, all of the little 0x numbers there are all the memory addresses where these are coming from. And so then you can track the shallow and retained sizes and get a better idea of how your memory is moving. So, and then here's another overview. This is essentially what I went over at the beginning is it's difficult to report DOM structure from a spider monkey perspective. And what we have done is made it so that we can report DOM structure from a spider monkey perspective and report it in enough detail to be useful and meaningful to anyone who's trying to measure this memory. So, yeah. Thank you. So, any questions?
Do you have any examples?
What kind of other stuff do you know about in Firefox that is still not visible to these tools that we could expand this out into?
That's a really good question. There's a lot of parts of Firefox that kind of like one that we've discussed is the cycle collector. It's a little bit ambiguous and it holds like I'm not an expert on the cycle collector, but it holds edges to lots of stuff that may or may not be useful, and it may or may not be actively used. It may just be floating around, and that is memory in the heap, that it has a piece of heap in there, and we could be reporting that once we can find a way to report it in enough detail for it to be actually useful to us. So, if that makes sense.
So I noticed that you, like, while describing how we're tracking all this memory, you've mentioned a bunch of data structures that you're using to track the memory. Do you know how much overhead the tracking adds to the memory usage?
So the UB node itself is designed to be completely lightweight. It's actually just a vtable and a pointer to whatever you're pointing to. So the entire structure of UB node is designed to be pretty straightforward and pretty lightweight, and things like getting edge names to yield to it or getting special elements to yield to it are all freed at the end of that heap snapshot cycle. So UBnode only exists in the scope in which you are using UBnode. And that was sort of how it was designed to make sure, because when you've got a memory tool that's measuring memory, then we don't want the memory tool to also be taking up memory. So that is sort of the concept we went into with that.
So just kind of follow up for all this. If I wanted to see this in action, how would I actually like see these reports and whatnot?
So when you're running Firefox, or particularly nightly, hopefully this will all be landed soon, but we have a menu up the top. I don't know if it has a fancy name or anything, but you click Tools, and you can go to a web developer, and it's a little menu. And we're not on the menu, but you can open up the web developer interface, and you can find there's a whole bunch of tabs. You can select memory, and then it has a little button that says take snapshot. You take the snapshot, and that is how you can explore your memory usage on your web page. What do we do?
We're done. Yep, that's it. Okay. Good job. Ooh, great work.
Presenting is scary.
You did great. Like, speaking of it,
Oh,
really
goodness.
hard.
Okay.
Yeah, good job. You can't do it.